this is an update, and as it being an update, it's sort of a compendium of a number of things that have essentially happened, both in the fusion community at large and also to me personally in the fusion community over the course of the last, I guess, 9 months. I guess August 30th was the previous update. So what I'm going to do is going to show you a few excerpts from some PowerPoint presentations, and then at the very end, there's a lot of slides, but I'm not going to show everyone, or I'll not talk about everyone. I'll zip through a few. If there are any questions, feel free to interrupt me, and then we'll get to this very nice video at the end, which is professionally produced by Commonwealth Fusion, so they know how to do it. Okay, so the outline of this is basically we're going to quickly review the fundamentals just in case anybody has come on board since the last one. You'll see a few of these things kind of come back in these various PowerPoint presentations. And at the very end, we'll have this video. Now, this is chronological. Basically, a lot of stuff happened in December. And then there's a jump, and then we talk about what happened really in June. And then there's kind of a backtrack a little bit here because of what I want to highlight what's going on just down the road from us, up Route 2 from us, if you want to call it that way, in Devens. And you'll see both some images, still images, and then you'll see this video at the very end. So the quick review is just in case anybody is interested. These are the two previous versions of the Fusion talk, Basics of Fusion, Part 1. That's the front page of it. And then Fusion Part 2. And these are the links. I can put those available as part of the presentation separately. So just to highlight the fact it's a hot topic, this was a talk that was given by Professor Dennis White of MIT. He's the director of the Plasma Science and Fusion Center, and essentially the instigator of why the facility is down the road there in Devens. This is a talk he gave at the Politecnico di Milano, and you'll wonder why the Politecnico di Milano is highlighted. Well, one of the major investors in the Commonwealth Fusion Systems, and by extension, one of the supporters now of the Plasma Science and Fusion Center, because the Commonwealth Fusion Systems signed a support agreement to give MIT more money than the federal government has been giving them in fusion for the first time. And because the Italian energy company ENI is one of the major investors in Commonwealth Fusion Systems. So he gave this talk up there, and I'll put the link on if anybody wants to see. It's a good, very good talk. And he highlighted a few things. One he highlighted was this work that had occurred in 2022, actually 2021, early 2022, at the National Ignition Facility at Lawrence Livermore, laser fusion or inertial confinement fusion. And then it was actually superseded by a press release that you'll see. A big story comes out later on in the year. There was also work at JET, the Joint European Torus in Cullum near Oxford, and they set a record for the amount of energy that was produced in fusion. These guys, but then also were competing against the fact that $1.8 billion had just been given in the end of 2021 to Commonwealth Fusion Systems. And they got on the front page of Forbes and some other things. Just to go back a little bit, the background of why Spark and Commonwealth Fusion Systems is interesting is because of this machine here. This is the Alcator C-Mod. It's the last in the series of Alcator machines. It's been shut down since 2016. at MIT. It produced the record amount of plasma pressure by having a very strong magnetic field. And if you want to see a tour of the thing, you can click on this link. I'll put that link in there too. It's on the YouTube. So what is it all about? Well, it's really all about right here. There's a composite force that occurs on any ions in the plasma that are trying to become part of the fusion reaction. At long distances, the ions are pushed back by just a Coulomb electrostatic repulsion. When they get close enough, they can climb over this potential hill, and there's an attractive, strong nuclear force which pulls them together and makes hydrogen into helium. So the net reaction with the breeding blanket that occurs over here is a deuteron and a lithium 6 or 7 basically ends up producing 2 helium. So it's a totally clean reaction. Now, there's a little details that are involved because the burning plasma produces a helium nucleus, an alpha particle, but it also produces a 14 MeV neutron, and that 14 MeV neutron is critical to 2 things. One is it provides most of the energy that is going to be extracted from the plasma. 75% of the energy is carried off in this 14 MeV neutron. And it also is critical because it has to be used to breed more tritium. Tritium doesn't naturally occur. I mean, it does, but trivial amounts of it. So we have to make it. Now we make it by taking that neutron and combining it with either a lithium 6 or 7. And you've got to do it very, very efficiently because you need 1 triton to combine with each deuteron, and you get 1 neutron out of it. It's not like a fission reaction where you get spare neutrons. So the critical thing that the breeder blanket has to do is make sure that it makes enough tritium to keep the reaction going. And in fact, you'd like to make a little extra so you can seed the next machine and stuff like that. So the thinking is basically that the breeder blanket will have 2 reactions. This one actually has 2 branches. And the key to this thing is this reaction, a neutron plus a beryllium actually fissions the beryllium, and the beryllium gives you 2 alpha particles plus 2 neutrons and a negative energy. It's an endothermic reaction. And then you basically then take these 2 neutrons and you make tritium out of the lithium. And you can do it with either lithium 6 or lithium 7, and so you don't have to have any careful amount of separation of the 2 lithium isotopes. You can just use naturally occurring lithium, or you can enhance it by putting a little more lithium 6 in there. Lithium 7 is the naturally dominant occurring isotope. This is the design parameters for a typical idea that people had for a fusion power plant a couple of years ago. It's changed a little bit since that time. The plant should produce somewhere around 250 megawatts of electricity. And in order to produce about 250 megawatts of electricity, it needs to essentially produce about 3 times that amount because the plant thermal efficiency is just at 40% essentially. So it needs to produce it. And this was the design for the ARC, which is the follow-on to the Spark, which you'll hear about more. And how do you solve this problem that we see over here is we use magnetic fields to confine this very high temperature plasma, because in magnetic confinement, most of the time the particles are still just bouncing off because of the Coulomb repulsion. They don't get close enough to actually be able to fuse. So you heat this thing up to the vicinity of 100 to 150 million degrees, depending on how you count the degrees and whatever. That means that the particles have enough energy that every once in a while they'll be able to climb over this hump. And the magnetic system is easy except for one problem. The particles are confined as long as they follow a magnetic field line. So if the field lines are open, the particles are confined along the field lines, but then they end up going out the ends. So we decide, well, back in the 1950s, we'll basically bend things around, make a circle, and the whole system becomes a torus. But the challenge then is to take into account the fact that the torus is obviously not an infinitely skinny spaghetti strand wrapped around the University of Wisconsin stadium, which is what they proposed in their first design, which was called UMAC 1. Because once you start to having a fairly sharp curvature, then the curvature is going to be demonstrably different from the inside and outside. And the particles will not be confined nicely, because as they go around the orbit, the field is stronger on the inside. So the orbit is squished on the inside and it's open on the outside at lower field strength, and the particles will tend to move outward as a result. And there's other things that happen, but that's the basis of it. So the various countries of the world decided to do this on a big scale, and they set upon building this machine called ITER. It used to be an acronym, but it's now basically been converted back to a Latin word that it was originally, because, of course, the Europeans always liked classical references for all their science projects and stuff. It's located in the Saint-Paul-les-Durance in France. That's in the Provence area, very nice place in France. Marseille, Toulon, and Monaco, Nice, these are all very close by, and they're all nice places to visit. It's the world's largest, or at least the European largest, construction project. This is a artist's view, obviously not the physical view of the thing. You can see the scale of it in some ways. This part here holds people fairly comfortably standing up inside it. And you can see the rest of the thing is several stories high because of the need for all the magnets and all the surrounding handling equipment. The power comes to heat the plasma. It comes from both radio frequency and particle beams potentially. So they provide for all that. This is what it looks like in the real world. This picture is a few months old. The tokamak building itself is this building right here. The surroundings are a giant power plant to provide, even though it uses superconducting magnets, it has all kinds of pumps and other things. And the heating process, you need a lot of energy for that. So there's all kinds of power plants, cooling towers, and all the works. Right. So back in the fall, students at both MIT and Columbia University participated in, I don't know, maybe the 10th version or something like that of this course that Professor Dennis White at MIT has taught, called the Engineering Principles for Fusion Reactors, also known as Fusion Design class. This is the first time that Columbia participated, that Princeton participated a few years ago. And you can get the YouTube video. I'll put the link in for that. I don't have it. I'm not going to play it right now, but I have some highlights. This is the most recent 10 years of it, and you can see how things evolve. These are the student challenges, and this is what the students came up with this time. They called it MANTA, for Modular Adjustable Negative Triangularity Arc. So it's falls in the great tradition of scientific and engineering acronyms that are actually acronyms based on other acronyms. There are a number of well-known ones, but I won't bother with it. One of the things that informed, excuse me just a second here, a bit of the coffee. One of the things that informed the design is a report that was produced by the federal government committee called the Consensus Study Report Bringing Fusion to the U.S. Grid. Came out in 2021. It has an organizational acronym attached to it, but ignore it. And the key targets for this U.S. fusion pilot plant was that Q, the scientific electrical output, would be greater than 1, not just the fusion energy being greater than the fusion energy going into setting it up, but actually the electrical energy would be greater than the electrical energy required, so that net electricity of about 50 megawatts for 3 hours would be achieved. And tritium breeding ratio, I mean, I'm sorry about all the acronyms, I should have put in a glossary. Tritium breeding ratio, or TBR, be 1 or higher for tritium self-sufficiency. That the cost for this system would be less than $5 billion, and that it could demonstrate successful operation through several environmental cycles. And in addition to that, there are educational goals to learn to use modern computational design tools to work in groups, but intertwine design features. And as these are the group leaders who were involved in producing the report. So the students looked at the problem based on the results of previous student excursions, and they looked at a large aspect ratio, low elongation, and negative triangularity design. Now, the negative triangularity is new for the students and relatively new for the fusion community. The idea of a D shape had been around for about 30 odd years. In fact, the General Atomic Company started it with a tokamak in San Diego called Doublet, which is now just called D3. It's one of the last of the early fusion machines that's still working. The most recent version of it. The scale of the machine is relatively small. You can see a person there by reference size. They came up with this idea of variable fusion power at a constant manageable diverter power exhaust. Now, the diverter is this stuff down here that basically exhausts the waste, which is helium gas and other non-waste but undesirable things like stuff that boils off the walls or something like that, from the plasma, to keep the plasma clean, and also to keep the power that's going to the walls to a minimum, so that the power is actually mostly exhausted through either the diverter or through the neutrons that come out, of course, carrying the bulk of the energy. They want to take advantage of the fact that it's a pulsed plasma, because continuous plasmas and tokamaks are not easy. Current drive is something that people have talked about, played with, but haven't been really successful yet. But they came up with the idea that you could just produce pulsed plasma energy, but essentially use thermal inertia to keep a constant electrical production output. And a very flexibly designed strategy to enable testing multiple designs and being able to test it through many environmental cycles, and of course, tritium breeding. So These were the groups. I won't go through all the details here, but you see core, magnets, power handling, neutronics, fuel cycle maintenance, integration, and economics. All these people worked sort of independently in their little groups, but they all came together just in time for the review, essentially. And you can see how the machine is constructed in that way out of 6 modules. This is new. Nobody else had thought about doing this. And as a result, it may inform people to actual real designs going into the future. These were constraints in terms of exhausted power. That was one of the things they were most concerned about. Won't go into the details unless anybody wants to know. The blanket has to be both cooled for the purposes of protecting things and also, of course, extracting the energy, because the energy comes out thermally. So the blanket captures heat, breathes tritium, shields the components. And they chose advanced, but what they call realistic materials to allow a compact, low activation vessel. Because one of the things that does happen, of course, is that with this enormous flux of neutrons coming out of the machine, everything will become mildly radioactive because of the neutrons banging into the atoms on the way out. So they viewed the fact that some of the components would need to be replaced. ITER has a major problem because of the design of the magnet. For ITER is essentially, well, I'm saying it's virtually impossible. It's very hard to replace components. But this thing is designed to have the magnet come apart at the seams, so you can replace the components as needed. And the clever idea was this power cycle outside the fusion world here, using this fluoride of lithium and beryllium mixture for cooling, and essentially using it with a heat exchanging system so that this Rankine cycle would actually provide the power, mechanical power, to drive the generator. And because of these 2 reservoirs here, you could essentially pulse this. Temperature goes up here, you cool it by running the Rankine cycle unit, and then you basically have enough energy there that this runs continuously, even though this temperature fluctuates. So from thermal storage from pulsed core to steady state, this is the novel thing. They may have patented it, I don't know. But it's clearly a novel idea. And they came up with an overnight cost of $3 billion, below the $5 billion requirement. And they said it was comparable to a electrical offshore wind pilot plant built in 2020. And this is how they compared their goals and achievements versus the NASM requirements. So Dennis White, as I said, gave this talk. And now we'll go on to the talk that I gave in Athens. I was actually in Lexington, but I sat up in the middle of the night and gave the talk to people in Athens and other people who were watching video in December. So we'll switch to that presentation. Let's see if I can do this right. How do I get out of this? I guess I go escape, and then I go over here, and I go here, and I go here. Everybody see my screen again? Seamless, relatively?
Yes.
Okay. So this was part of a bigger invited plenary talk that we had. I'm sorry?
Spaceport song.
You're right.
Ted, what does overnight mean when you talk about overnight?
Oh, okay. There are multiple different ways of costing big projects. One is a life cycle project cost, which would go on for 40 years or whatever the lifetime of the thing would be. Another one would be the cost as delivered of the equipment and stuff like that. And the overnight cost is basically what it would cost to deliver it and have it operational. There's a more precise definition, but that's effectively the definition, as opposed to the life cycle cost. That's the two bounds essentially you want to compare.
Thank you.
Yeah. So we gave this talk as part of this conference, DESERT, which stands for Dependable Systems, Services, and Technologies. It's been going on for a couple of decades. It principally was organized by people from Ukraine, from Kharkiv in Ukraine. The principal guy behind the whole damn thing essentially is Vyacheslav Kochanski. He's a good friend of mine, a colleague and co-author, and also author of a book that I have a chapter coming out in a few months. And he's been involved with aerospace and nuclear systems of high reliability for a long period of time. Michael Yastrzębinecki, have trouble with his name, and I shouldn't have that much trouble with his name. But if you think of sort of like Karl Yastrzębski, and I had the Benetsky at the end, in the middle of it there. Anyway, he's essentially in Kyiv in Ukraine at the State Center for Nuclear and Radiation Safety. Andrzej Roshinsky at the University of New Hampshire, emeritus professor now, and he spends half a year in Poland. I was with him on Skype yesterday, and we'll be on again today. And he's in Poland right now. I'll be back in New Hampshire at the end of the summer. And Professor Koen van Gulich, who is originally from the Netherlands, from the name, obviously, but is in Huddersfield in the United Kingdom right now. And this was the outline of the talk that we gave. We talked for a little over an hour. And this is my piece right here. I had a little piece of this, but the primary piece was here. Practical fusion energy is a foundation for global safety and security. And I called it the new Promethean gift. It was in Athens. You'll see there's a little over the top here, but anyway. So just to put it in the context, this was Roshinsky's slide. He insisted on using these two pieces with me. This is when we visited as part of the UNH program for students doing microelectronics systems development. We visited DEC in Hudson, Massachusetts, back around 2008 or 9, something like that. That's me over there. And the big guy in the middle is Roshinsky. And this is, that's Roshinsky and Harchenko. This is at Chernobyl. And that's the Chernobyl secure facility that they built over the remnants of the reactor there. This is Roshinsky on the beach, and it's either in New Hampshire or Poland, I don't know. And this is a talk I gave on energy in Poland last July. That says the national capital, and it's a pun, capital being like financial capital. This is a interesting one that Roshinsky has used many years. This is in the Christa McAuliffe Planetarium in Concord, New Hampshire. That's a satellite that Roshinsky's students built, never launched, but it's hanging in the over there. So this is how he finished up, and he pushed that picture again. So I like that picture there. It's a actually 19th century Prometheus image. And the challenge, basically, that's what this says, new Promethean gift over here. The key remaining challenge to delivering practical fusion energy as a foundation for global safety and security is proving that the decades of science experiments can scale to a functioning reactor. And this is a drawing. It's not a photograph. There is no photograph as far as we know of Fermi's pile number 1 in Chicago at the University of Chicago Stag athletic facility there in 1942. So can you get from there, which is where we almost are, to, there's a close-up of it, to a commercialized reactor. These are 3 commercialized reactors. And the one I chose to illustrate is the one that used to be there in Rowe, Massachusetts. Essentially, if you again follow Route 2 west, that's the Connecticut River that is flowing through there. And it used to sit on the shore there, and it was very nice looking building and everything like that. Came about around 1960. So it took almost 20 years to go from what was the first working reactor to the first practical power plant. Now, the shipping port was a little before that, and Dresden was even a little before that, but neither of those actually followed with a design that you could commercialize, really. This was a naval nuclear reactor, and this was a breeder experiment, basically. So I went with this Rowe one. That's a good picture of it.
Ted, just to be clear, these are fission reactors.
These are fission reactors, correct? So they're just being used as a model, essentially, what it takes to get from a working reactor to a commercial reactor. And in one, you have to say at least 15 years based on any measure of the timing. And one of the things that this project had going for it was, of course, during World War II, it was a very high priority to make a successful reactor that could actually produce plutonium. That was the major reason why Fermi was doing what he was doing in Chicago. And they, of course, built the Hanford reactor facility in Washington state to produce the plutonium that was used in most of the bombs that existed until the hydrogen bombs came along. Even then, some. Yeah. So the benefits, of course, of this, the new Promethean gift, are, I think these are my personal observations. I think decoupling the fuel availability and state of development is important, because not anybody could do this, because you needed access to uranium that was enriched sufficient to run a power reactor, at least, not necessarily necessary to produce a weapon, but power reactor. So that limited the access to the fuel. If you look at the state of development, the necessary state of development to put in a nuclear reactor is still pretty high. And some of that has to do with safety requirements and things like that. It offers dependable, essentially inexhaustible. Obviously, inexhaustible is a word that's not a scientific word, but it's a pretty good sense of roughly 1 billion years worth of hydrogen in the ocean, maybe somewhat less of the lithium, but a lot. Planet might not be around in 1 billion years. We don't know. Anyway, it can scale, and it can basically be done at a small scale, city size power plant, 150, 200 megawatts electrical, to a complex with many reactors and gigawatts of power. And it's available on demand anytime and anywhere. You can't say that about the other kinds of renewables, if you want to call it that. So here's a quick review of fusion again. fusion is why it's worth doing, why fusion's been hard to do. Fusion and tokamaks, traditionally the path from the T3 machine in the Kurchatov Institute near Moscow via jet to ITER, and then the MIT Highfield way from Alcator to ARC via Spark. The challenge of converting the fast neutron flux from the core to electricity. You absorb the neutrons in the blanket, you breathe tritium, the blanket gets hot, and the hot blanket then is used to drive a traditional turbo system. One of the things that's advantage of a fusion reactor core is that in principle, you could take an existing power plant that's a thermal power plant and move a fusion reactor into the site and screw it on to the pipes that go to the generator, the alternator and generator, and it would be perfectly fine. So again, because it was Athens, I said, voila, well, that's French. And everybody calls this Eureka, but having studied a little ancient Greek, it's actually Evreka. Electricity for the grid is in English. So quick summary again, E equals MC squared gives you lots of energy for a small amount of fuel. I like this diagram. It's unfortunately I can't find the reference to where I got it from. It disappeared into the mists, but it shows you everything. Reference comparison purposes, 1,000 megawatt coal-fired plant requires 2.7 million tons of coal per year. 1,000 megawatt fusion plant would require 250 kilos of fuel per year. Kind of different. And, single gallon seawater, everybody's heard this one probably. Minimal nuclear waste. There are some issues with respect to the disposal of some of the irradiated components, depending on how you make the components and what you make them of. Some things have longer half-lives as just neutron activated materials, but by and large, no significant issues. Minimal nuclear proliferation issues. Some people say, well, you can use those neutrons coming out of there to breed plutonium, even if you don't have a nuclear fission reactor. That's probably true. These neutrons are fast neutrons, so you have to moderate them some, but it's possible to still do it. In any event, this is a repeat of this thing, Coulomb thing, magnetic fusions. Some of those are the same pictures you've seen before. So this is what a tokamak looks like in an artist's conception of a schematic drawing. The old style ones had iron yokes, made it clearly as transformer, even to somebody from a high school level of understanding of things. Modern ones have done away with that. There's just this core here now. This was the original. There was a T1, but the first one that anybody ever heard about was the T3 at the Kurchatov Institute. First time I heard about it was a little after that, because the Soviets were keeping it secret until 1968, when there was an international conference and they opened it up to everybody. Everybody was skeptical until the British went there with some laser scattering experiments to measure the actual temperatures, and said, well, they're actually telling the truth, which was kind of surprising at the time. JET basically is direct follow on to this thing. In last year, the European researchers, and it's complicated now, of course, because JET, when it was built, was part of Europe. Now it's kind of a thing that's being licensed to Europe in a sense, because the British left Europe officially, or European Union in any event. This is what they did a little over a year ago. Whoops, go back to that. If I can get back to that. 59 megajoules. This is what the inside of jet looks like. Pretty much any tokamak nowadays looks pretty much like that. Different scale of it maybe, but otherwise the same. These things right in the center here are protection for the actual first wall of underneath it. And in some places there are specific things sticking out even farther that are called limiters. In other places they use a bend in the magnetic field and they call it a diverter. But the idea is to keep the first wall from being really cooked. This is the actual data from the experiment. Fusion power, they had previously done this where they actually produced an output in 1997, and in 2022 they doubled it essentially, a little bit more, and the duration was 5 or 6 seconds. But the problem is to make it a commercial reactor. When you turn it on, it draws 575 megawatts through essentially a special connection to the transmission grid to power the copper magnets. And when JET operates, they have to basically clear in advance with the National Grid Authority that they're going to turn it on, because some people might have to turn off their, not only the air conditioning, but some of the factories and stuff in the area. This is what, sorry.
Ed, can I ask a question here? You're comparing 59 megajoules and 575 megawatts.
Yeah.
I know you mentioned the duration, but I didn't catch it.
Okay, it was well, you can see it on the screen here. It's the total pulse length was essentially 7 seconds. The square part of the pulse was about 5, so it's roughly 10 megawatts.
Okay, so it's a factor of 50 maybe.
Yes.
Negative payback at this point.
Correct. Correct. There are some other things that require some power, but by comparison to this, not much. So this guy unfortunately passed away essentially about a month or so after this record, but he said a sustained pulse of deuterium-tritium fusion at this power level, nearly industrial scale, delivers a resounding confirmation to all of those involved in the global fusion quest. The ITER project, the JET results are a strong confidence builder that we're on the right track as we move forward towards demonstrating full fusion power. Unfortunately, since that positive statement about ITER has had some problems. They had to remove some pieces that had been installed at great effort because they were defective, and that sets them back a little further than their original schedule and their second schedule and their third schedule and their fourth schedule. So I think they may be on track to be operational around 10 years from now. They originally were planning to be operational by now, but that's 20 odd years back. This is JET's work over its history. They started putting it together in 78. It produced the first deuterium-tritium experiments at full power that anybody did, and it produced those 21 megajoules. And then they installed this new beryllium tungsten plasma facing wall. And see, this brings up the issue. This is good stuff from the standpoint of taking care of the plasma and taking care of the wall, but it's not the best thing to put there if you're going to bombard it with neutrons. The beryllium will produce extra neutrons. Maybe that's good in a sense for the breeding process, but the tungsten will get fairly radioactive. And anyway, so this is the record 5-second average power. Yeah. That's what the JET experimental hall looks like. The machine itself is in here. picture on the inside again. This is a scale drawing, so you can see the size of the human versus the jet machine. In order to handle the radioactive components, this is a person actually inside the machine. They decided they needed a robot, so the Cullum people have been developing some very advanced robots to handle pieces that are radioactive. They're sort of become a world leader in that now. So here's the ITER comparison. That's jet. This is ITER. Same size person. Supposed to be the same size person. And that's the construction site. That was a little earlier than the other one I showed. And this is all the extra stuff that you need to get from the fusion core to electricity. So you need to, of course, process the stuff produced in the blanket, because some of the stuff you produce in the blanket is helium gas. What you're looking for is tritium gas. Then you have to extract it and then be able to re-inject it back into the chamber. And meanwhile, you have to extract the heat energy and power your generators. And this comes from the original doublet, or D3 now called D3D version of it, from General Atomic. They've been in the fusion business as a company longer than anybody else. This is from the MIT Plasma Fusion Center and with CFS. And this is the MIT approach. So you start with the CMOD, you go to these are current devices. Well, CMOD shut down, but D3 and JET are still there. Here's ITER. Here's demo, because ITER doesn't actually produce any real power for the grid. It produces several hundred megawatts of fusion energy, but you have fusion power, but you have to put it to a bigger scale yet to make it run the grid. The MIT approach is you go from CMOD to Spark. It scales up a little bit, and then you scale it up a little further to ARC. And they think it can deliver the first plasmas in Spark next 2 years from now. And then Q greater than 2 soon after. The goal is to have Q greater than 10. There's Alcator. CMOD, the original Alcator, which not too much smaller than this, was the first tokamak I worked on, and when I was an MIT undergraduate back around 1972. CMOD set the world record on its last shot for the greatest plasma pressure, which broke the previous record that they had. 2 atmospheres plasma pressure. Temperature was not really hot enough, 35 million degrees C, but it did produce 600 trillion fusion reactions. That's what Alcator, as I said, looks a lot like JET on the inside, a little smaller. And this was the record high pressure discharge. So that's the plasma pressure in atmospheres. This was the plasma temperature. This is called the sawtooth relaxation oscillation. And part of my PhD thesis was involved with those kind of things. This is unwrapping the wall, the outer wall of the torus, so you can see different parts of it, what they do. These are structures for introducing electromagnetic waves for heating. That's what keeps the plasma off the wall. There's a diverter structure. There's more of it over there. Another set of electromagnetic wave antennas for different frequency. And this is what was achieved in the 50 years essentially since fusion became serious, I guess, in a sense. Start over here on this axis. This is the product of the density of the fusion ions and the time that you confine them. And this is measured in cubic meters per cubic meter seconds. So the goal is to be somewhere up around in the 10 to the 20 to 10 to 22 range. This is the temperature of the ions. You have to be realistic in this range up here between 10 and 100. This is measured in kilo electron volts. You can think of this as 10,000 degrees Kelvin per electron volt. So this is 100 million, that's a billion. The sun actually operates way down here, but it has gravity to work in its favor as a confinement means. So this is much bigger over here. In any event, Model C, which was the second Alcator, the first one was Model A. It really is just sort of down here somewhere. It's not plotted on this thing for some reason. That followed the Alcator A machine in basically around 1974. The C mod, which is the machine that set the records, these are the two record shots over here. This is ITER right here and Spark. They're both trying to get to this goal, is to be Q. This is Q on this axis, or the ratio of the power that goes in to power out, or energy goes in, energy out, depending on how you're counting things. You need to make this big, ideally infinity, but certainly at least 10 or 20. And ITER and Spark get in that range. Some of these things over here, say Omega and FireX and Nova and stuff, those are inertial confinement things, laser fusion. This is the National Ignition Facility and the most recent results that they've got. So here's this one-page summary of the MIT thing. The magnet that's been tested, the design is the Spark, then they go from the Spark to the arc, and some people working on things in the lab. So the key is the high temperature superconducting material. High temperature superconductors were a big physics story in the 80s, 86 breakthrough. First time you got the temperatures that were essentially liquid nitrogen, almost temperature, as opposed to liquid helium or liquid hydrogen. But those things were very hard to work with. They were brittle and they were very hard to see how you're ever going to make a good magnet out of them. But things happen over time, and by about 10 years ago, people were commercially starting to sell samples that looked like this. This is a sandwich of copper on the top and the bottom, Hastelloy or stainless steel in the middle, and a very thin layer where it says Rebco, about 1 micron thick of the high temperature superconducting material. Some critical density versus magnetic power density, current density versus magnetic field. The old superconductors fell off very quickly when you applied a magnetic field, and that limited things. And that's why ITER is as big as it is, because they chose to use low temperature superconductors, because when they essentially finished fixing the design, the goal eventually is to get to ARC. This was the plan for ARC. First generation plan may be different, but Spark design has been sort of scaled up in this case just to make ARC. The key is here, magnet joints allow vertical maintenance. So you can take it apart with a crane as opposed to having to be essentially a magician, I guess, to take it apart without taking the magnets apart. Schematic diagram. I'll skip that, skip that, skip that. So here's Spark as a test bed for ARC. Spark will not be producing electricity, but it will provide the information you need to get to ARC. Here's where existing experiments lie, and this is where they think Spark will be, and there's ARC. Prometheus one more time. This is a notional path to practical fusion energy. They think they'll have it operating as a tokamak in 2025, 2027. They start DT testing, and they think in 2027 to 2030, they should get to Q greater than 1, which would be essentially equivalent to the state of the Chicago pile. The ARC prototype plant construction would begin possibly in this era if there are no weird surprises and stuff like that, and operational akin to the shipping port of Dresden or Yankee could be 2030, something like that, maybe 2035. They'll have power on the grid. So that's what they were saying a few months ago when they showed that picture. That's the tokamak hall there. Because it was Athens and Christmas time, that's a Greek Christmas card. Very nice image there. Yeah. Okay, so anybody have any questions so far? Because the next thing we're going to talk about actually is laser fusion.
From what you're saying, it looks like Spark is going to be equivalent or maybe even better than either.
Well, the design parameter is very similar in terms of output and stuff like that. The most important parameter, though, is how long, how much, and how usable. That's kind of a summary of the thing. ITER will produce useful science, I think. There's no question about that. May produce useful engineering. Will not produce a useful path to the thing, because if you follow the path, you go up to demo, you're talking about a machine that small countries would require their entire gross domestic product to achieve one machine. And, that's one machine. Spark to ARC, again, assuming there are no curveballs in the middle of the thing, that's a much more achievable thing. That's a commercially fundable thing. You can get, they've raised $2 billion so far. To double that, that's easy on the commercial market, financial markets these days. So this is, let's see if I do this.
Quick question.
Yeah, sure.
Concerned about the fact that you're putting in, you're doing confinement in the KeV range.
Yes.
And you're getting output of particles in the MEV range.
Mm-hmm. Yes.
You're making conversion, some of that conversion into heat for driving the electrical power grid and so forth. But I still don't quite understand how it is that you can control this to the point of the confinement when you've got a factor of 1,000 more products coming out than you're trying to confine. So I don't see how it continues. I can see where you get a pulse.
Yeah, so that's actually one.
I don't see how you keep it going.
Right, that's actually one of the sort of open questions in a sense. I mean, what people have done so far is produce short duration examples where they've produced a fairly substantial amount of fusion energy being released in the form of the neutrons that they see coming out, and also presumably the alpha particles that are confined well enough that you're keeping the amount of heat in the plasma. And that so far has not been proven to be the case yet, because all of the experiments to date have required auxiliary heating that's continuous even during the period of time when you have the fusion reactions going. So the alpha particles are not heating the deuterons and tritons sufficiently yet to actually have a continuing reaction. That's challenge, because as you pointed out, the energy of the alpha particles is, let's be charitable and say, because the most of these heating schemes produce a tail on the ion distribution function. So some of the ions, a fair fraction of them, are going quite a bit faster than the average. So that means that if you're saying that the temperature of the deuterium and the tritium is on the order of 10 to 15 keV, you probably have quite a few particles in the 50 to 100 keV range. So then the 3.5 MeV alpha particles, not really going that much faster, because remember, of course, they're 4 times heavier. So they're effectively equivalent to a 1 MeV kind of a deuteron or a triton, in a sense, or maybe 2, something like that. So there's a factor of 10 to 20 in there, not the hundreds, but it is an issue, because confinement is, of course, designed to work with a sort of a homogeneous kind of distribution of particles, and it hasn't been tested yet. That's still to be shown. So that's an issue. As far as the desire of having a machine that lasts for a long time compared to the confinement time, to prove that's coming, I think, pretty soon. But it's not here yet. Jet doesn't really do that. It's confinement time, and their duration of their experiment was, within the factors of 5 or so. That's not really sufficient yet. But Spark will do that, assuming everything works. So now we'll take a look at.
Can I ask a question first?
Of course.
There was a time when the blanket needed to be renewed. Is that time past?
Well, depends. There are different kinds of ideas for blankets. The MIT plan now seems to be using this liquid blanket, which is a molten salt of lithium fluoride and lithium chloride that are chemically in a equilibrium, basically, and that basically has the advantage that the renewal of the blanket is just pumping more stuff into the tank, whereas these other blankets that people are talking about, refueling the blanket is harder than trivial, let's say, because nobody's done it yet. So this is I'm sorry.
The time scale I remembered for that was weeks.
Yeah, it could be weeks or it could be months. Yeah, and that's one of the challenges, again, because if you look at the way ITER is put together, those big magnets basically have to be shielded by this blanket structure surrounding the vacuum vessel, because you don't want those neutrons bombarding the magnet material, because that, especially with the low temperature superconducting magnets that they use, that'll kill the superconductivity. So you have to put the blanket in between the magnet and the vacuum vessel. It makes the magnets bigger, and of course it makes removing things from inside the magnets more challenging.
Thank you.
Yeah.
So
Question.
sorry. Any other questions?
Yeah. You were mentioning that lithium chloride and lithium fluoride would be used in the blanket.
Yes.
They're pretty damn corrosive. How is that going to be handled?
That's an issue, obviously, and the students looked at that as one of their challenges, and they think it's manageable. Nobody's really done it yet, So we don't know for sure, but they think it's manageable. They are, it's a fairly exotic material, molten salt of that kind of active
What
metals.
are they confined in? I mean, that the corrosion, that's where the
So
corrosion.
in the MIT design, there's a blanket tank, and the magnets and the blanket and the first wall, the whole thing basically sits inside the tank. If you have to service things, you can open the top of the tank, and whatever the walls they'll end up with for that tank is obviously a material that has to meet a number of criteria. Obviously, can't be magnetic because it's inside. Very strong magnetic fields are present around there. So it has to be something that's non-magnetic. It has to be something that's thermally able to handle the high temperatures, and not the keV, but the hundreds of degrees C, and obviously has mechanical issues as strength and stuff as well. And then there's the corrosion. So that's a challenge. That's still to be developed. So this is the cover of the 70th year report from Lawrence Livermore Laboratory. And they're very happy to tell you about everything they did over 70 years. And I just quickly summarize how they got involved in inertial confinement fusion. It started in 1974. And I saw this laser operational, started in the early 80s. I was still doing fusion at that point. And then they came up with the idea that the primary reason for them being there, of course, is nuclear weapons. And so they said, yeah, we can sell to the DOD people and the Department of Energy, as it became known by that time, that we can help measure the performance of the weapons without them having to do tests in the desert. So they said, okay, then lasers can sort of mimic what goes on inside a nuclear weapon. At the same time, they decided to build a national ignition facility. Look at that date, 1995. In 1997, they imagined how thermonuclear physics and matter at extreme conditions could be linked together to sell it to the people who pay them the money. And by 2009, the National Ignition Facility was operational, dedicated, and it was focused on the stockpile stewardship, which meant how do you keep track of what's already in the stockpile of weapons to make sure they keep on working. And then also this high energy density science as a sidelight. In 2013, they decided that they really could do something with fusion because they had developed targets for the weapons program that could be sort of declassified. And by 2021, they said they were at the threshold of fusion ignition. In 2022, they got on the front cover of Nature. And they had a paper, Burning Plasma Achieved in Inertial Fusion. There's 150 authors or something here that goes from Hopkins to Zimmerman in alphabetical order, pretty much. This is what they said. They obtained a burning plasma as a critical step towards self-sustaining fusion energy. Then they said that after decades, they're there, very close. Facility delivered 1.9 megajoules of energy in pulses with peak powers of up to 500 terawatts. By the way, it takes 400 megawatts continuously for a while to charge up the power that's going to be released as 1.9 megajoules in 500 terawatts. So the lasers spend a lot of time charging. They make a few shots a day at the best. And the key is that they use the lasers to heat the inside of the cavity to indirectly drive the compression, because the direct compression that was worked on in the early days by Livermore and also by Rochester, it doesn't work. You have to go back to the Teller-Ulam design for the H-bomb, and it looks like this. All the lasers basically produce a plasma that emits X-rays, and the X-rays then do the actual compression. Multi-layer structure here, which has pushers and ablators and all kinds of stuff, and then on the inside it's got some DT vapor. And when you do that, this is the amount of power that's coming in from the laser, and this is the so-called Hall room. This whole thing is called the Hall room. Radiation temperature. So the Hall room basically heats up in the EV range. So they depend on the really high density to overcome the fact that the temperature is not nearly as high as it is in the magnetic fusion. This is what they claim sort of for their little plot of things. They talk about hotspots and, you know, a lot of esoteric stuff, but the key is that they follow this trajectory, and these are the most recent things that they've done, and they think they got really close to ignition if they didn't get there. And then in December, they put out this press release, and it's, well, it's a great press release, ignition. But when you take the numbers here, you say, well, that's not really akin to, well, Fermi's pile number one produced about 5 watts worth of equivalent energy output. And this thing, while it produced megawatts, the duration was so short, you would have to be firing these things at hundreds of times a second. And, you know, they can right now fire a couple times a day if they're lucky. This is what the target chamber area looks like. It's a very fancy facility. Quote from Granholm. This is the business part of the thing. That's the holder for the hall room. That's the hall room itself. If you go back to this picture over here. And then this is a kind of a actual combination of a photograph and some artistic work, because you can't really be there when those lasers are firing, obviously. And even you can't even have a camera there. These are some of the people who participated, besides all the people from Lawrence Livermore. Even the universities doing tokamaks and stuff got involved, like MIT and Princeton. And UK Atomic Energy Establishment and the French Alternative Energies and Atomic Energy Commission. And so anybody have any questions about that? And then we'll go on to the finale here. No? Okay. So
I have another.
This is PR, mostly.
excuse me?
You're saying this is PR, that mostly?
Yes. Well, I mean, it's a real achievement, obviously, but to go from that achievement to something that could be a commercial reactor is a huge leap. It's akin almost to saying, here we have the temperature that they achieved, essentially 1 keV in T3 back around 1970, and where are we now today? Well, you know, it took 50 years to get from T3 to where we are today. It could take that comparable here too. Now they have things they say, well, these lasers they're using right now are glass, neodymium glass lasers, and they have better technology and stuff like that. They pump them with old-fashioned flash lamps, and maybe pump them with diode lasers, and all these things can make the efficiency more reasonable from the standpoint of electricity in to laser output. But this facility inside here, just that, is essentially a manufacturing marvel in the sense that the precision necessary to complete this inner compression part is extraordinary. You have to be down in the sub 1 wavelength of light at the laser frequencies and stuff. So can you make thousands of those per hour or hundreds of thousands per day or whatever? Who knows? It's well beyond my pay grade.
Question. Why are they calling this a hole realm? I thought that meant vacuum or black body.
Well, that's the origin of the name. It's German, one of these German sort of acronym contractions almost. This is it here, right? So all these lasers come in, and all that energy gets bouncy around inside here, boils off the inside walls, makes this plasma that basically then radiates X-rays that, of course, are not going to be confined by the walls, but will be radiating in a way that essentially produces a virtually isotropic compression. So, it meets the criteria of the kind of the name, if you want. Tiny little hole here, lots of energy inside. Kind of a black body.
Okay, thank you.
Yeah.
Yeah.
It was funny when I went to see the place. There was a Division of Plasma Physics, the American Physical Society meeting, and I was given a paper there. And we got a tour of Livermore because the meeting was in San Francisco, and so get on a bus and you ride to Livermore. And after we saw the facility, they put us in this room to wait for the bus to show up because of security relations. And these two guys got up and they started scribbling and sort of arguing and pointing at each other and whatever, writing on the board. And then a person came in from outside, told everybody no one had ever been in this room, nothing had ever been written on the board. The two guys who were going at it were the director of the lab and his counterpart in the Soviet Union. If it was secret, what the hell did it matter to the two people? The polar opposites of from the governmental standpoint are having a scientific discussion. Who else are you going to share it with?
Sure, it wasn't budget numbers.
Yeah. And they're talking in English too.
I have a problem. It's a fairly simple problem with this scheme as a practical means of generating electricity, and that is you've got to charge. Think of it as charging capacitors, which is what they do.
Yeah.
In order to get the power into the lasers.
Right.
Takes a long time to charge these capacitors.
Oh yeah.
And then so how do you make this an industrial process?
I don't think you do. I mean, I think you have to, make a number of other steps along the way because, yeah, of course, part of the reason you take a long time charging capacitors is you don't want to blank out the entire Bay Area. 400 megawatts in one spot, that could be a problem. So to put the 400 megawatts into the lasers, into the flash lamps for the lasers, you basically put it in at a megawatt or something like that. And you just take, the better part of an hour to charge them. But as I said, the cooling is a bigger problem. So they only can fire a couple times a day at the max. Okay, so
as a practical matter, they're using glass lasers, and glasses have very bad thermal conductivity.
Yeah.
So removing the heat from from those laser materials is a real problem.
Well, they acknowledge that. They don't claim that this is one step away from the finish line, except if you're, somebody from Washington. And then when there's somebody from Washington, they'll agree with the person from Washington, obviously, because they want to keep the money coming. But anyway, so this was a talk. I don't know how much longer do we have.
We have like about 8. It's 2. How long is the talk?
Okay, well, these are slides from the talk, so I'm just going to highlight 2 slides, and then I want to show the video, which takes about 2 minutes at the end. Okay, so this was a talk that was given at the MIT Tech Reunion in June. 2 professors from the Plasma Science and Fusion Center and from departments physics and also nuclear and also nuclear engineering. And they started off, this was kind of interesting. There was a technical problem. The PowerPoint slides were not available. So in the good MIT professorial fashion, not on a whiteboard, but on a blackboard, and they started writing. And the class listened. As soon as he got his go ahead, he had his, I don't know, MacBook or whatever it was there, and he started his slides. So there's a lot of slides are very similar. I'm just going to skip by, but this is an interesting way of measuring it, comparing chemical energy, sugar, about 17 kilojoules per gram, coal about 24, gasoline about 46, so roughly a factor of 3 between sugar and gasoline. Fission about 1 million times what you could get per kilogram from gasoline, and fusion, because of course it's hydrogen, about another factor of 7, so about roughly almost 15 million times more energy density in fusion than in gasoline. And the advantages, everybody, same thing. Fusion is hard, same thing, pretty much. This is a slightly different way to present that same stuff I showed before, but it points out in one slide, hot, dense, and confined for a long time. Lawson, triple product. Lawson wrote a paper in 1957. It was classified at that time and then finally released, even though it was given to the British Proceedings of the Royal Society, but it was a classified paper. How to confine it. You can use electric fields, magnetic fields, or gravity. Sun uses gravity. We don't. Magnetic confinement, pretty much tokamaks, and then you can also achieve the same kind of effect by twisting the magnets in a way to produce a twisted magnetic field. That's called a stellarator. It may come along the way. It's a little behind in terms of where it's achieved things. That's ITER. There's spark. These are approximately, this is a comparison to scale, and that's a little bit different scale than this, but more detailed. Inertial confinement, there's the laser stuff. This is, he's a European guy, so of course he liked to be classical, so he's a Quo Vadis, famous novel by Henryk Sienkiewicz about the journey of Peter to Rome, and where are you going? Remarkable results: magnetic confinement, jet, inertial confinement, NIF. There was a bold decadal vision for commercial fusion energy PR exercise out of the White House. UK did the same thing toward fusion energy strategy. These things produce paper documents also. This was disappointingly slow but vibrant. Well, not so vibrant now. Some problems since the time this slide was made. This budget request is currently still there, $1 billion for the fusion budget in the U.S. And the commercial sector is now raised much more than the federal government has put in over the last decade. Technical problems still to be solved. So this guy is a computational physicist and a theorist, and he looked at this thing from the standpoint of plasma confinement. Everybody else is taking that sort of for granted. If you back away from these parameters that are known to be sort of the boundaries of unstable operation, you can be okay. But the losses are still much bigger than predicted by simple models. And so can you get better at that? So he thinks that's still one problem. Heat extraction, that's still an issue because diverter is exposed to heat loads of up to 10 megawatts per meter squared, which, as he said, is comparable to spaceship during atmospheric reentry. So the rest of the walls are not being hit very hard, but that diverter area has a target area for basically dumping the energy and the exhaust, and that does get hot. Tritium breeding, he pointed out the fact that you've got to basically be really efficient in it because it's never been tested yet. One idea is this neutron multiplying idea, which is the beryllium, for instance, again, not been tested. And then there are some exotic ideas that don't involve neutrons, but they're still ways away from where we are. And then he pointed out that there's some regulatory regulation and social acceptance issues. There is no internationally accepted regulation for fusion energy. The US, however, has taken the lead, and the Nuclear Regulatory Commission has decided that fusion is now in the same class as a hospital radiation treatment equipment. So you need some shielding of the immediate vicinity, but you don't have to worry about long-term radiation. But there are social issues. Fusion has got the word nuclear in it, and people have to learn about this a bit. So what he said we're doing at the PSFC, developing the superconducting magnets, investigating tritium breeding. There's a thing called Libra, developing and supporting other diagnostics at the NIF, pioneering quantum computing because that's simulating is still very hard, and educating. There are a big, huge crowd of people now are graduate students and some undergraduates at MIT and working on fusion. And as he pointed out, as a side note, that can quantum computing help? This is the IBM quantum computer. Maybe it makes sense. Maybe it helps. This is these are the people in the audience here, showing how a very good crowd, very interested in what's going on. And his conclusion is fusion has unrivaled potential, but it's hard to do still. And he says a vibrant field, significant challenges, still thinks tokamaks is the first to reach commercialization. And then a little plug for Plasma Fusion Center. So the other professors from nuclear engineering, Mike Short, he pointed out there were really three things that he said need to be de-risked: magnets, tritium, and materials. So I won't go through all this because it's some it's redundant. High field magnets, scaling, you can see the scaling. This is the high temperature superconductor. That was these slides. I was supposed to get copies of the slides and I didn't. So far I'm using photographs I took, and then I've extracted a couple pictures that covered some of these things. So this is what this thing looks like. It's a pretty sophisticated technology in itself. So you start off with 20 microns of copper. You lay down on top of that 1.8 microns of silver. This is cast alloy or a stainless steel-like material for structures, 50 microns. Then there's a bunch of buffer materials that are sort of a top secret for the people making these materials. 0.2 of a micron of it. And then a micron of the rare earth barium copper oxide superconductor. And then on top of it, the same stuff. And the reason you do the same stuff on the top and the bottom is as you wind this thing, this is what it looks like when you wind it. That's a person's hand for reference purposes. This is an artist's conception of this stuff being added onto it. This is what it looks like. And you wind it so there's no insulator. And it takes a little while to get used to it, but the fact is that all these things up until you get to here at superconductor temperatures are very, very resistive compared to the superconductor. So all the current flows in the superconductor. A little current flows in here. A megawatt or two of power is dissipated in the magnet, but it's nothing like 500 megawatts. This is the big difference between ITER and spark. This is a low temperature superconductor. The range of current density, temperature, and magnetic field. I think somebody made a mistake spelling. And this is the high temperature superconductor. All these directions are stretched. And this is where people are with respect to superconductors overall. This is over here. You can see that's the surface of Pluto. This is liquid nitrogen right here. And this is the backside of the moon, or nighttime on the moon. So some of these things, YBCO, that's right up here, it can operate in principle at temperatures of close to the surface of the moon. So you could build a reactor without any cooling. Problem is, of course, to make it really work well, you can't be at all these at the same time. You end up backing down here to somewhere in this vicinity, liquid neon, or maybe even liquid hydrogen, in order to get the maximum of the magnetic field and current density. This was the lab that used to hold the fusion experiments at MIT. Now it's basically the test facility for the magnets. That's a picture of what the magnet looks like. This is the test facility for it. And more of this. Path to fusion energy. This is where it stands with respect to construction. They've tested things. They're starting to build the magnets in the next few months. They built the prototype magnet, but this is what the facility looked like a little while ago. You'll see on the video what it looks like now. Tritium, still some issues there. Obviously, you've got to be really good at this process of converting the neutrons into tritium. This is, in case you haven't seen tritium, well, you're not actually looking at tritium, you're looking at tritium exciting something to fluoresce with the beta particles coming off the tritium. So here's the breeding you have to do. This is the lithium beryllium fluoride, and these are estimates of tritium breeding determining the timeline for the fusion energy market penetration, because you got to make enough stuff not only to power your own reactor, but to produce some tritium to bootstrap the next one. So different types of blankets have different sort of tritium doubling times. Conventional blanket seems to go on forever. The liquid immersion blanket so far looks very promising. So the MIT is building this thing, the world's first ton-scale net gain tritium breeding experiment. I say, well, if you've already done that, well, it's of course using an external source of neutrons, and but it will breed enough tritium that they'll be able to measure the efficiency of the tritium breeding process with the blanket design. It's called Libra. It stands for something or other, I don't know, but it's not obvious what it is. And materials obviously are an issue, as we've been talking about. One of the things that,
Ed,
yeah.
Ed, it's running a little late, a little more than your estimate.
Okay, let me just run the video then, because that kind of wraps everything up very, very nicely.
Perfect.
Okay, small. Let me.
6 months ago, we moved into Davis, Massachusetts, which is our corporate headquarters, our magnet factory, and our Spark facility. This is the site that we're building. This is an actual building full of equipment, making parts, making assemblies that are going to go into a fusion machine that's being built right behind me.
In this factory, we're building the 3 main superconducting magnet types for Spark. I think it's a pretty incredible feat to see how far we've come in the last 6 months. My team has grown now to 150 people. That's more than double where we were in December. This was a brand new factory that we just moved into to now have these production lines behind me producing actual parts that will go into Spark.
So the company 6 months ago, was really quite a bit smaller. And now it's all here, a large space to be able to make our own, and to have that energy on the site is really important. We're trying to show that this technology can be an option for climate change. The hard part about climate change, it's slow, but it's huge. And your only lever on it is to get scale. You need speed in order to get scale, because we have to basically outrun it. And so that means it's all about speed. So over the next 6 months, we're going to go from debugging the lines to actually running them. And that's the way we build up the magnets that we need to install in Spark. And then in 6 months in Spark, we'll actually start to see the first components go in, of the actual tokamak, into the tokamak hall. There's nothing like coming to this campus. You show up and there's a factory and there's a lot of people working really hard to do that. And then there's a facility that's a fusion machine that looks like a plant, and it is a plant. It's big, but not too big. It's industrial, but not too industrial. And to see that happen so rapidly is really, really compelling.
That's it.